Let's continue our talk about logarithms. First, recall a logarithm is the reverse of an exponential function. What do we mean by reverse? I mean, if I give you the point xy, I'm going to flip it over and make it yx. Here's the graph of 2 to the x. I graph the points -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. Now let's reverse that. That means I'll have 1/4, -2, 1/2, -1, 1, 0, 2, 1, and 4, 2. Let's put those points on the same axis we have with 2 to the x. So at 1/4, I'm at -2, and then at 1/2, I'm at -1. At 1, I'm at 0, 2, I'm up to 1, and then over to 4, I'm up to 2. We're going to connect these dots. Now, as we connect these dots, we're thinking we're doing the opposite of 2 to the x. So I can see here's this nice curve that's coming along from connecting the dots. And I want to do the opposite of what 2 to the x did. So 2 to the x ran along the x-axis. So my opposite is going to run along the y-axis. So everything opposite. Now we said this first graph is 2 to the x. What the second graph is the opposite, which is the log base 2 of x. Let's talk more about what logarithmic functions look like when we graph them. I have the same graph at the bottom, my log base 2 of x, but it kind of generically looks like any log base b of x if b is greater than 1. Big properties to point out. Number 1, x is greater than 0, so everything is over on the right side of the y-axis. My function is increasing, kind of slowly, but still increasing. It's going to cross the x-axis at the point 1, 0, missing my 0 there, and it's going to have the point b1. So the points 1, 0 and the point b1 are going to be really helpful when I go to graph. I'm going to connect those dots and then just kind of curve my graph over. Let's graph f of x is log base 3 of x. When I go to graph, I really only need 2 points. I need 1, 0, which we said the graph's always going to cross the x-axis at 1, 0, and then the base, which is 3, is going to be up to 1. So I go over 3, up 1, there are my points. Remember I told you x is always going to be positive, so as I'm drawing, I'm coming along the y-axis over to the x-intercept, picking up that point 3, 1, and then just curving it. Let's do it one more time. Here's log base 7 of x. Again, I'm going to have 1, 0. I'm going to have 7, 1, so my base with 1, and I'm going to keep my x's positive. So 1, 0, my x-intercept, 7, 1, my second point, come up along the y-axis, pick up the intercept, go up and pick up the other point. That creates my curve. Let's look back at the definition of logs just so we kind of review what we're doing here. So the log base b of y equals x means that b to the x is y. I introduced this as thinking, when you say log, I want you to think power. I want you to think what power of the base is my number y. So everything is powers when we're looking at logarithms. Let's just get more familiar with that relationship between logs and exponents by rewriting these equations. So the first one says the log base 4 of 16 is 2. So writing as an exponent, the base becomes the base of my exponent. What's on the right side of the equal sign, that is my exponent, and that will be equal to 16. You can see that that's true, 4 squared is 16. My second one says the log base 9 of 1 is 0. The base, again, 9. On the right side of the equal sign, I have a 0, so that becomes my exponent, and the answer is 1. C, I have the log base 5 of 1 over 25 is -3. My base is 5. My exponent is -3. That gives me 1 over 125. The last one, I have the log base 8 of x is 3. I wanted to throw one in there where the numbers aren't all there for you just to make sure we get the idea. So the base is 8, the 3 becomes the exponent, and that's x. I'm not going to solve because that's not what this problem said to do. Now let's just do that opposite. Let's reverse it. I'm going to rewrite these as a logarithmic equation. I have 4 cubed is 64. The base, 4, becomes the base of my logarithm. 64 is what I'd be taking the log of, and the exponent is 3. Second one, I have 7 to the 4th is 2,401. So 7 is the base of my log, 2,401. That's what I'm taking the log of, and my exponent is 4. 3 to the negative 4 is 1 over 81. So think about, what's our base? Our base would be 3. What am I taking the log of? 1 over 81. And what does that give me? It gives me negative 4. Last one, I have 6 to the 5th is x. So I have the log, my base, that would be 6. What am I taking the log of? X. And what's it going to give me? 5. I have a couple kinds of logs I want to talk about that are on your calculator, which is always a good thing. The first one's called the common log. So common log is base 10. What happens is when we use common log, we don't write the base. So if you see a log and it looks like the base is missing, that means it's understood to be 10. So when you see the log on your calculator, that log represents log base 10. So it's up to you. You could just grab your calculator now and evaluate these expressions that I've given you. The log of 1. What this is saying is, what power of 10 gives me 1? It would be 0. Think about 10 to the 0 is 1. This says, what power of 10 is 10? It's 1. I'll write it for you. Then I have 100, and I'm thinking, what power of 10 is 100? That's just 2. And then 1,000, well, that would be 3. What's fun with log base 10 is that I can see when I'm looking at powers of 10, it's like I'm counting the zeros. There are no zeros for 1. There's 1 0 with 10, 2 zeros with 100, and 3 zeros with 1,000. Same thing if I go to do decimals. I can think about the log of 0.1 is really 1 over 10. How did I get to be a fraction? I made it a negative exponent, so the log of 0.1 is negative 1. The log of 0.01, very similar with the idea there that we could think about 0.01 is really 1 over 100. Let's write it the right way. So this is the log of 1 over 100, which is negative 2. At any point, if you want to grab your calculator, and I think you should just try these out, you can see that the log of 0.001 will give me negative 3, and the log of 0.0001 is going to give me negative 4. So let's look at some that are not perfect powers of 10. So this requires you to grab your calculator. Let's go ahead and do these to 3 decimal places. So I want you to find the log and then put in 17. You should get 1.23 and then 0. I said 3 decimal places, so we want to go to that third one. The log of 9,875. So I have log 9875. This gives me 3.99. I said 3 decimal places. So on my calculator, I see 4, 5. This third number, I have to look at the 5. It's 5 or bigger, so this means I'm going to make it 3.995. Then I have this small one. I have the log of 0.0257. It says negative 1.590. Another log that's in your calculator, it's called the natural log. What it is the log base e. So instead of writing the e as the base of the log, we're going to write ln of x. Again, let's grab our calculators. That'll be the easy way to do it. We've talked about e before, and remember every time we went to access e, we got it from using that ln button, so that natural connection is there. So go ahead and hit the natural log of 1. You should get 0. What does that say? It says e to the 0 is 1. the natural log of e. So you're pushing the natural log, and then you're also having to push that e to the x button. If your calculator is where it says e to the x, and you're like, okay, I have ln, and now I'm at e, and it's looking for a number, put in a 1. It's going to output 1 for you. Then I have the natural log of e cubed. That's going to give me 3. What's happening here is all of these questions are saying, what power of e do I have? Well, e is the first power of e. E cubed is the third power of e. So it feels a little repetitive, but we're just pulling that exponent down. Okay. So just like log, because natural log is also in your calculator, I can give you any kind of number and have you evaluate the natural log of it. Again, let's go ahead and do 3 decimal places. So let's start with the natural log of 154, and that gives me 5.03695. All right, I wrote more so we can just make sure we remember how to do these rounding. So 1, 2, 3, I'm looking at the 6. The 9 says I want to go up, so I'm going to make this 5.037. Let's try again. Natural log of 34,891. It says 10.45998. All right, 1, 2, 3. Here's my third number is a 9. I look beside it. I also have a 9, so that says round up. That's going to round this 9 up, which makes that one go over. So I end up with 10.460. One more. Natural log of 0.05. This gives me negative 2.95573, right? Again, I'm just making sure we know what we're doing. 1, 2, third one. I'm looking at the 7, so this becomes negative 2. Let's erase that stray mark. All right, so now we have negative 2.95. And the third one, that 7 is going to go up and make that a 6. A few quick properties that are kind of helpful, and we've used them, but let's just talk about them separately. The first thing is the log base b of b is 1. So anytime the base matches the number we're taking the log of, it's going to give me 1. Like the log base 12 of 12, it would be 1. The log of 1 is always 0. So again, no matter what the base is, so say I had the log base 11 of 1, it would be 0. And then finally, the log base b of b to the x is x. All log says is what power of b do I have? And if I have the log base 8 of 8 to the 7th, well, what power of 8 do I have? I have 7. So let's try that with a few different logarithms. So the first one, I have the log base 5 of 5. Now notice that matches, so the 5 and the 5. So what power of 5 do I have? 1. Then I have the log base 4 of 4 to the 7th. So this 4, 4 matches. I bring the 7 down. The log base 9 of 9 to the 3.5. Hopefully you're going well. I know that's 3.5. And the last one, log base 8 of 1, that's going to be 0 because everything that's the log of 1 is 0. A little bit of a twist on that. Now I'm giving you an equation, and I said let's solve for x. So I have the log base 3 of x equals 5. I'm immediately going to rewrite that as 3 to the 5th is x. So I'm going to use that connection of the definition of logarithm. I'm going to turn it into an exponent. Once I have it as an exponent, I can put that in my calculator, and that tells me that 3 to the 5th power is 243. All right, same thing. B says log base 2 of x is negative 6. I'm going to rewrite that. I have 2 to the negative 6 is x. Well, remember negatives say I really have fractions, and I think this is the way you should do it. If you put it in your calculator as 2 to the negative 6, you're going to get a little decimal. You're going to have to switch it back over and make it into a fraction. So this way maybe you can avoid that one extra step, and you can just say 2 to the 6 is 64. But up to you, you can do either way. C says log base 7 of x is 0. So 7 to the 0 is x. That means x is 1. And then finally, the log base 8 of x is 4. That says 8 to the 4 is x. I take 8, I raise it to the 4th power. That says x is 4096. All right, so how about a little application to say, why do we even talk about logs? So here's the first formula. The time it takes a population to double can be found by the equation t equals the natural log of 2 over r. So let's answer a couple questions about that. First, how long will it take a population to double if it's growing at a rate of 5%? First thing I want to do is say 5% is equal to 0.05. So this time is going to be the natural log of 2 over 0.05. So when you're given a rate, turn it over to a decimal. Now I'm going to put in the natural log of 2, and then I'm going to divide by 0.05. This is going to give me 13.86. Let's go ahead and make it 3 decimal places, which is 3. This is typically in years when you're looking at population doubling time. When you put natural logs or any kind of log in your calculator, it may put a parenthesis in when you first do it. Make sure you close it before you divide by 0.05. If you got a different answer than the 13.863, that's probably what happened, so you want to stop, do it again before we go to the next one. Let's just change the rate here. Let's say, well, how long is it going to take a population to double? If the doubling time, or the rate, is 0.08. So we have this rate of growth of 8% a year. We're going to say, how long does it take to double? So this is natural log of 2 divided by 0.08, and this says 8.664 years. This is important. Like, say we're some city, right? And we're looking at our population's growing. If the population doubles in about 8.5 years, you're going to have more housing, more food, you're going to have more cars on the street, you're going to need more schools for kids to go to, right? So there's reasons to look at population, right? We're going to have more jobs for these people to work at. So lots of things, lots of people care about this doubling time. Here's another thing I think kind of makes sense for especially in the summer of how hot things get. So this function f of x is 13.4 natural log of x minus 11.6. This models the increase in temperature inside a car after x minutes when the temperature outside is between 72 and 96. So if it's colder, it would be different. If it's hotter, it'd be different. What this means is you're driving around the car, you park it, and you go, right? It's going to heat up once the car's turned off and we don't have our AC on anymore. So let's say it's 94 degrees outside, and we want to know what will the temperature be inside the car 15 minutes after we leave it. All right, so we're going to say this is f of 15. This will be 13.4. This will be the natural log of 15 minus 11.6. So 13.4 is from the function. The 15 is how many minutes later we're looking at what's happening. So let's put that in our calculator. 13.4 times the natural log of 15. Make sure you close that parenthesis and then say minus 11.6. And this gives us 24.68. Okay, let's go ahead and just make that 25. When I have this, it's not going to be 25 degrees in the car. It's going to be 25 degrees higher, right? We said we started at 94, so we need to add 94 and 25. So 94 plus 25 says this new temperature, it's 119 degrees inside this car. Let's try that again. This time let's plug in 40. So f of 40, I have my 13.4, natural log of 40, minus 11.6. So in my calculator, I have 13.4 times the natural log of 40, make sure you close the parenthesis, minus 11.6. This gives me 37.83. I'm going to say again, let's just go ahead and round that to a whole number, and I'm going to make it 38. That 38 needs to be added to the temperature outside of the car. So 94 plus 38 equals 132 degrees inside that car. This is why we don't leave our kids in the car, we don't leave our pets in the car, right? It gets really, really hot really, really quickly. You can see 15-40 minutes is not a lot of time, right? So way too high, way too fast.